Welcome back to section 9.4, the second part of mathematical induction. We are now going to look at example 3, and for this example we have to prove that this summation, 1 times 1 minus 1 plus 2 times 2 minus 1 plus 3 times 3 minus 1 plus n times n minus 1 equals the equation of n times a quantity of n minus 1 times a quantity of n plus 2, all divided by 3, are actually equal. So as you recall from the principle of mathematical induction, the first thing we have to do is we have to prove that s of 1 is equal. So if I take and I plug a 1 in, and again I'm going to do this over on this side here, if I plug a 1 in for every n, I end up getting 1 times 1 minus 1 times 1 plus 1 divided by 3. 1 minus 1 is 0, times 1 times 2 is still going to give me 0 in my numerator divided by 3, which is 0. Now if you come and you look at this term right here, this is really your first term. Sorry here, let me rewrite that. This is your first term, or your a sub 1 term, and if I simplify that, 1 minus 1 is 0 times 1, so that first term also equals 0. So because I get 0 here and 0 here, I can say that step 1 checks. So now let's move on to part 2. The first thing I'm going to do, I'm going to go ahead and replace every n with a value of k. So I end up with s sub k is equal to 1 times 1 minus 1 plus 2 times 2 minus 1 plus 3 times 3 minus 1 plus, and then I have the quantity of k times k minus 1, which is equal to k times k minus 1 times k plus 1, all divided by 3. Now I have to go through and prove that s sub k plus 1 equals this stuff. I'm going to plug in a k plus 1 over here for every k, so equals k plus 1 times k plus 1 minus 1 times k plus 1 plus 1 divided by 3. And again, I'm plugging in a k plus 1 for this k plus 1 for this k, and a k plus 1 here for this k. So when we simplify that, I'm still proving that s sub k plus 1 is equal to k plus 1 times k, which I'm going to pull out up front, times k plus 2, and I'm going to divide that all by 3. So now, in order to prove that s sub k plus 1 is equal to all of this stuff, I have to come up with what s sub k plus 1 equals. So I'm going to go and look at this half of that equation. So s sub k plus 1 tells me that I'm going to have 1 times 1 minus 1 plus 2 times 2 minus 1 plus 3 times 3 minus 1 plus all the way up to k times k minus 1 plus, now I'm going to replace every k in this with my k plus 1 because that is the next term, which is what I'm looking for. So I'm going to have k plus 1 times k plus 1 minus 1. So if I simplify that, we get 1 times 1 minus 1 plus 2 times 2 minus 1 plus 3 times 3 minus 1 plus, I end up with k times k minus 1 plus k plus 1 times k. So from here, if you look at this value, or all of this stuff right here, this is all equal to this first piece right here, which we called S sub k. So I can call all of this S sub k. Now because S sub k was defined up in our original equation as also being equal to k times k minus 1 times k plus 1 divided by 3, what that tells me is I can now replace this S sub k with this value up here that was given to us in the very beginning. So I now have k times k minus 1 times k plus 1 divided by 3, and I'm still having to go through and add this k times k plus 1 because this is the next term. Now I'm at the point where I have to prove that this stuff here is really equal to the original right-hand side of the equation with the k plus 1 substituted in, or this k times k plus 1 times k plus 2 divided by 3. So I'm going to go ahead and set those equal to each other right now. So I have that as k times k plus 1 times k plus 2 divided by 3. Now I'm just going to go ahead and simplify my left side of the equation and make it, well, hopefully everything works out, but it should come out to be the right-hand side of my equation if I've done everything correctly. So let's go ahead and simplify this piece here. So let me select my pen. So I'm going to simplify this side first. Now to add two fractions, if you recall, we have to have that common denominator. And in this case, I can see that my common denominator is 3. So I end up with a k times k minus 1 times k plus 1 divided by 3 plus 3k times k plus 1 divided by 3. And again, all I did is got the common denominator for this fraction. So if I simplify, and I'm going to stick with simplifying just my left-hand side right now, if I simplify this, I see real quick that these two pieces here are going to give me k squared minus 1. So k times k squared minus 1 is going to give me k cubed minus k divided by 3 plus, and now I'm going to simplify this, which is going to give me 3k squared plus 3k, all divided by 3. And if I simplify that, now that I have two denominators that are the same, I can go ahead and add and subtract all the like terms. So I end up with k cubed plus 3k squared plus 2k, all divided by 3. And if I simplify this, I see I can factor out a k. So I have k times k squared plus 3k plus 2 divided by 3. And let's just bring this up over here for now. So now if I factor my k squared plus 3k plus 2, I see that I've got k times k plus 1 times k plus 2, and I'm still dividing all of that by 3. Now what I just did is we found that this, which is still our left side, is really equal to this up here, which is my right side. So because I was able to prove that the left side equals the right side, I can now say that I proved this formula by mathematical induction. Now, within this section, we do have a special set of summation formulas called the sums of powers of integers. These are given to you on page 679 of your textbook, but an example of one of them, and we're going to use this in the next example, this is number 3 out of that table there, says that if I have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, and so on, or in other words, I'm cubing n, that this is the same thing as taking n squared and multiplying it by the quantity of n plus 1 squared and dividing all of that by 4. So I'll show you how to use this in the next example, and I will give you these formulas on a test or quiz. You are not required to memorize these. So for example 4, part A, we want to find the sum from, and I apologize, this here should be an I equals 1 to 7 of I cubed. Now because I cubed is one of those sums of powers of integers, we can go ahead and use the formula. And if you have your book open or recall, that I cubed was equal to n squared times the quantity of n plus 1 squared divided by 4. So all I have to do now is I have to plug in my n and then simplify this equation. So n in this case is 7. So I have 7 squared times 7 plus 1 squared divided by 4. This is going to give me 49 times 64 divided by 4, or if I simplify all of that, then you'll see that you end up with 784 as a final sum. For part B, if you take a look here, oops, let me get my pen turned on, you'll see that from that sums of powers of integers table, you'll see that you have a formula that gives you a sum for I and for I squared. So what we need to do is we need to break this 6i minus 4i squared up into 2 summations. And we can do that by factoring out the 6 up front, and I'm still going from I equals 1 to 4 of I, and then I'm going to subtract 4 times the summation from I equals 1 to 4 of I squared. Now what this is going to simplify to is 6 times, now the formula for I is just n times n plus 1 divided by 2, and then I'm going to subtract 4 times, and I squared is going to give me n times the quantity of n plus 1 times the quantity of 2n plus 1, and all of this is going to be divided by 6. So from my summation, I can see that my n value is 4. So I'm going to plug in a 4 for every n. And when we do that, we end up with 6 times 4 times the quantity of 4 plus 1 divided by 2 minus 4 times the quantity of 4 times 4 plus 1 times 2 times 4 plus 1 divided by 6. And then we simplify, we end up with 6 times 4 plus 1 is 5 times 4 is 20 divided by 2, which is 10, minus 4 times, I end up with 4 times 5 times 9, all of this is divided by 6. So this gives me 60 minus 4 times 30, which is 60 minus 120, or a negative 60 for final solution. The last thing we're going to look at in section 9.4 deals with finite differences. Now we did talk about these back in Algebra 2. However, I realize that's been quite a while, so we're going to go through an example. And the first difference of a sequence can be found by subtracting your consecutive terms. Now, if we get the same number when we subtract these consecutive terms, then we can say that we have a linear model. If they're not the same and I need to go and do a second difference of the first difference, if I do a second difference and I get the same number, then I have what we call a quadratic model. And the pattern is going to continue on. However, for the sake of our problems, we're going to stop with either linear or quadratic models. So let's go and look at example 5. So we want to find a model for the sequence with 0, 4, 10, 18, and 28. So to do our difference, I'm going to look at these two terms, and I'm going to go 4 minus 0, which gives me 4. I'm going to look at the difference between my next two terms, which is 10 minus 4, or 6. The difference between my next two terms is 18 minus 10, or 8. And my last two terms is going to be 28 minus 18, or 10. So this is my first difference. Because these are not the same number, that tells me that this is not a linear equation or a linear model. So I'm going to try to do the differences again. This time, when I subtract these out, 6 minus 4 is 2, 8 minus 6 is 2, and 10 minus 8 is also 2. So this is our second difference. Now because I finally obtained the same difference for my consecutive terms, this tells me that I have a quadratic function, or I can write a quadratic model for this set of data. And if you recall, a quadratic model, or a sub n, is equal to an squared plus bn plus c. So we're going to use this to help us create our model. Now because I was given my 0, 4, 10, 18, 28, and so on, these are my a sub n terms, because I know that my first term, or a sub n, or a sub 1 equals 0. I know that a sub 2 was 4, a sub 3 was 10, and so on. I'm going to use that bit of information to help me come up with this model. So for my a sub 1 term, I know that a sub 1 was equal to a times 1 squared plus b times 1 plus c, and that all equaled that first term, which was 0. My a sub 2 term was equal to a times 2 squared plus b times 2 plus c, which was equal to 4. And my third term, or a sub 3, was equal to a times 3 squared plus b times 3 plus c, which happened to equal 10 in this problem. So now we need to go ahead and simplify all of this. When we do that, you'll notice that you get a plus b plus c equals 0. Then we have 4a plus 2b plus c equals 4. And then we have 9a plus 3b plus c equals 10. So hopefully by now you recognize that you have three equations with three unknowns that can be solved either using methods that we learned to solve three equations with three unknowns, or you can use matrices. I'm going to assume that you're going to use matrices, and we'll set up our coefficient matrix of 1, 1, 1, 4, 2, 1, and 9, 3, 1. I'm going to multiply that by A, B, C, and I'll get my constants of 0, 4, and 10. And if you remember, this is my A, X equals B. So to solve for A, B, and C, I need to go A inverse times B will equal X. By typing this in your calculator, we can find that A equals 1, B equals 1, and C equals a negative 2. So, for my model, I know that my model should read that A sub n is equal to 1n squared plus 1n minus 2. And here's my model for the set of data that was given. So now, to the time that you guys have all been waiting for, we are going to look at the meaning behind the phrase true colors. And this is coming from I Didn't Know That by Carolyn Evans, the book. It says, the original true colors were shown in the flags of early sailing ships. Pirate legend has it that many a good ship was conned into believing it was approaching the ship of a friendly nation because of the flag it flew. However, once the ships were within cannon shot of each other, the pirate vessel quickly changed its flag, showing its true colors, just before looting its victims. So now, if you go on Jeopardy and that becomes a question, hopefully you can win. And if you do happen to win, don't forget where you learned that fact from. Have a good day.